Hey everyone, I'm gonna go through 5.6 for you today, so get ready to follow along, maybe take some notes. But basically, we're solving equations today that involve logarithms that aren't going to be, I guess, as easy as the ones that we did in 5.3. So yesterday I kind of left off. I did not do this last problem, but I also think it's a very good problem to start with before we get to 5.6, because we're going to talk about how we can solve some more equations with logs in them. Seeing this example at the bottom of the last page of 5.5, we have log base 3 of x minus log base 3 of 2x plus 1 equals log base 3 of 4. Solving log equations is similar to solving exponential equations, where if you have log equals log and the bases match, we know that the insides match. This is a very similar thing to a to the x power equaling a to the y implies that x equals y. So if we can rewrite this equation so that we only have one log on the left, one log on the right, we can actually solve this. So think back to our log properties. When logs of the same base are separated by a subtraction sign, that we can put together using division on the inside of the logs. So we can rewrite the left-hand side as log base 3 of x over 2x plus 1, and that's going to equal log base 3 of 4. And just like with exponential equations, when you have this log base 3 and log base 3, when that matches, we know the insides have to match as well. So we know that x over 2x plus 1 has to equal 4. We multiply by the denominator to cancel that. Don't forget to distribute. X equals 8x plus 4. Negative 7x equals 4, and x equals negative 4/7. As always, with logarithms, you have to double check your answers. It's nice just being like, algebraically, we found the number that makes things work. But if we plug in negative 4/7, do we get a positive result when we plug things in back into the original equation? Here's a problem. In the original equation, we have log base 3 of x. If we plug in our negative 4/7 into there, it does not work. So even though algebraically that number is a solution, this equation has no solution. So I'm going to get the next page ready. I'll be back in a sec. Alrighty. So just like that problem previous, we're going to be working with solving where we have logarithms and exponential stuff in these equations. We're teaching it during the log or after logarithms because it's not going to always be as easy as our exponential equations. Sometimes we're not going to have same bases and all that stuff. But basically, what are we looking for? We're looking for, can we get bases the same for exponentials? Can we get bases the same for logs? Can we write it as one log on each side, same base? And if not, if we just have log base a of x equals y, then we can go back and forth between the exponential form. These are the things that we're thinking about today. So looking at number 1 right here. I see multiple logs, but I see same bases. Your best bet here, combine them. Using our log properties. Subtraction leads to division inside the logarithm. Now, we don't have a logarithm on both sides, so we're going to turn this into its exponential form. The base of the log is 3, so the base of the exponential is 3. Squared equals x plus 2 over 2x minus 1. I'm going to pause, see if that makes sense, solve for x. When I unpause, which will be momentarily for you, you'll see the answer, but make sure to try it. So you pause your video, I'm going to pause mine and come back in a moment to see what the answer is. Okay, so we had 3 squared equals x plus 2 over 2x minus 1. 3 squared is 9. Doing a little bit of algebra, canceling denominators, combining like terms, moving things from side to side, we get 11/17, which when we plug it in, everything's positive, so we're good. That is our solution. Take a look at number 2. It is super similar. I know I just asked you to pause, but I think it'd be a good idea if you paused and tried to set this up. I'm going to pause, set it up, so if you just let it play, you'll see it set up real briefly here. All right, I'm hoping you paused. If not, you get to just see the work. So we combined the logs because they're the same base. Addition leads to multiplication inside the log. Log, even though we can't see the base, is 10. So we turn it into the exponential form. 10 to the power 2 equals x times x plus 15. This is quadratic. 10 squared is 100, so moving things over, we get 0 equals x squared plus 15x minus 100, which factors to x plus, I'm blanking, x plus 20, x minus 5. And then our solutions to that algebraically are negative 20 and 5. But thinking we have a log of x, we can't plug in negative 20 into log base 10 of x. So we have to throw that out. Our only answer is x equals 5. That is our solution there. Number 3, we got 3 logs going on. Logs on both sides, which generally means to me it's going to be a little bit easier because we'll be able to set log on one side equal to log on the other. But again, how about you take a pause for a second, you try to set it up. I see logs on both sides, so your goal is 1 log on the left, 1 log on the right. See if you can set it up. I'm going to pause and write mine too. Okay, I'm back. We combined the 2 logs on the left through multiplication on the inside because we're adding logs with the same base. You'll notice that we get log base a and log base a on both sides, so we can take their insides and set them equal. So x times x minus 2 equals x plus 4. And then kind of hurrying through this solution, x squared minus 2x equals x plus 4. I see quadratic again. Move everything to one side. X squared minus 3x minus 4 equals 0. That factors to x minus 4x plus 1. So our solutions are 4 and negative 1. Check both of these. Here's what I notice. Plugging in 4, everything's okay. Plugging in negative 1, again, this log right here, you can't, no matter what a is, you can't have log base a of negative 1. So we have to throw away our negative 1, so x equals 4. I do want to say that negative numbers sometimes can be solutions. Don't always throw them away. Just check to see if we can plug them in. We've had to throw them out every time because we've always had a log base something of x, and you can't. If x is unchanged, then we can't have negative numbers. All right, next page. Exponential equations that require us to think about logs sometimes. So check out these little clouds at the top. It's really important that you read them this time. If we can get a common base, you already know how to solve these. If you can't get a common base, we're going to convert things to logarithms. Going back and forth between those things is going to be helpful. This first one, you look at it, you should probably have an understanding of how to solve this. So I'm going to go through it quickly. 81 is 3 to the 4th. Common bases, we get 2x minus 1 equals 4. X equals 5 halves. I'm hoping that one is kind of familiar. We look at number 5. This one threw people off on the quiz. This 4 times thing, man, is that tricky. We can get common bases, though. I see 4, 8, and 32. Those are all multiples of 2. 4 is 2 squared. 8 is 2 to the 3rd. 32 is 2 to the 5th. And what people made mistakes on the quiz is doing 4 times 8. 4 times 8 to the power 3x plus 1 is not 32 to the power 3x plus 1. When we multiply same bases, we add exponents. So please be careful with that. Common error made on the quiz. Be careful. See our common bases? I'm actually going to write one more step. This is 2 to the power 9x plus 5. And this is 2 to the power 5x plus 10. So we got same bases. So we get to go over to 9x plus 5 equals 5x plus 10. We get 4x equals 5. So x equals 5/4. That is certainly a weird looking 5 up there. My bad. So we haven't gotten to anything that we're not familiar with. And then we get to number 6. 5x equals 14. 5 is a prime number. 14 is 7 times 2. We cannot get common bases. So how would we start solving this? What kind of number would we even know what to do with x? This is where we use logarithms. If you can't get a common base, turn it into a logarithm. The base of the exponential is going to be the base of the logarithm. We flip-flop where the x in the number is, so it's going to be log base 5 of 14 equals x. That's the answer. Log base 5 of 14 is a number. Do I know how to calculate it by hand? I certainly do not, which is why I have one of these. If you go to your calculator and do log base 5 of 14, I'm sure this won't focus really nicely. If you look at my face up in the corner, I'm holding up my calculator for you. The answer, the number, is about 1.640. X is approximately 1.640. If you type that into a calculator, 5 to the power 1.64, you get just about 14. A little bit off because we're rounding. So this is a number. I know it doesn't look like a number and it doesn't register to our brains that it's a number, but log base 5 of 14 is a number. That's the exact solution. This is the exact solution. This is the rounded solution. Log base 5 of 14 is about 1.64. So turning things into logarithms is going to help us solve equations. So when we look through this last page of problems, we got what, 5 on this page? I want you to look at number 7. It's very similar to what we just did. You should pause and try this out before you come back to see me work on it. Did you pause? I hope you did. E and 4. You're not going to get common bases with E and 4. It's not going to happen. So when we can't get common bases, we turn it into a log. Log, the base of the exponential is e, so I'm going to write log base e. I'm going to flip-flop the other things. 4 equals x plus 1. Now, I told you yesterday, no log base e's. I want you writing this as ln of 4. Now, to get x by itself, just subtract 1. Be careful here, folks. That 4 is inside the logarithm. When you subtract 1, this is not natural log of 3. This is, you have to keep it like this. If you want to write parentheses to help you understand, it's the natural log of 4 minus 1. Whatever that number happens to be. I'm going to go back to my calculator. Natural log has a nice button, so I'm going to click ln of 4, put my close parentheses minus 1, and we get the value of about 0.386. So you want the rounded answer? It's about 3 or 0.386, but the exact answer is the natural log of 4 minus 1. And then we get to something like number 8, and something like number 8 is a killer, okay? We have exponents on both sides. This is a tough problem. It's really hard to think about this, rewriting it into a log, so I'm going to kind of do this in a slightly different way, which technically is the same thing, but it does not look like the same thing at all. Here's what I'm going to kind of give you a hint with. Take a log of both sides. So you know how we're able to like multiply both sides by 2 and things are still equal? We can raise both sides to the second power. Both sides are still equal. You can take the logarithm of the left and a logarithm of the right, and the equality still holds. You will see naturally when math teachers do this, they'll either just do log or ln. I'm going to do this problem through ln. So I'm going to take the natural log of the left side, and I'm going to take the natural log of the right side. Now, why would I do that? That has just made more stuff appear. You have to think about what our log properties are. Inside of a log, if we have a number raised to a power, what can we do with that power? We're going to use our log property of exponents to bring that exponent down to the front for both of these. Ooh, I wrote something wrong. I'm sorry about that. The exponent on the 5 is 2x minus 1. Sorry about that. I'm actually not going to write parentheses around that 5. So here, we've gotten x out of the exponent on both sides. Now, I'm going to walk through this whole problem because there is a lot of algebra to do here, and it looks really confusing. And I'm hoping you're able to kind of take it step by step and not get too worried. So first of all, we have to distribute. So we get x times ln of 3 plus 2 times ln of 3. On the other side, distribute the natural log of 5. 2x times the natural log of 5 minus the natural log of 5. If you think back to how we were doing inverse functions, how are we going to solve for x? You need to get everything with an x on one side. You're going to factor it out of all the terms, and then you can divide away the other stuff. So I'm going to do a little rearranging. Everything with an x, I think I'm going to move to the left, and everything without, I'm going to move to the right. So see if you follow here. We're going to subtract 2x ln of 5, and we're going to subtract 2 times ln of 3 from both sides. I'm going to write it once. But I'm doing it from both sides. We get x natural log of 3 minus 2x natural log of 5, and that's going to equal negative 2 natural log of 3 minus natural log of 5. And I'm kind of squeezing that in there, sorry. Everything on the left-hand side now has an x, so we're going to factor it out. So we get x times the quantity ln of 3 minus 2 ln of 5. That is equal to negative 2 ln of 3 minus ln of 5. And then to get x by itself, we can divide by all that junk to get our final answer of negative 2 times the ln of 3 minus ln of 5 over ln of 3 minus 2 ln of 5. Hot dog. Is that a mess of an answer? This is the answer, though. This has a value. Off the top of my head, do I know what the value is? No, not a chance. But if you give me a second, I'm going to pause my video. It's not going to really pause much for you. I'm going to type it in my calculator to tell you what it's approximately equal to. I just needed a moment to type, and I wasn't going to make you watch me type. I type everything in, I get about 1.795. So even though I can't tell just by looking at it, this is approximately 1.795. You go back to the start, you plug in 1.795 in for x, you'll get about the same thing on both sides of the equation. This problem is a toughie. Taking a log of both sides is some pretty challenging math, I'm going to be very honest with you. But there's an example of it, and you're going to try your best when you see other examples in the future. The last three problems go together. I'm going to show one, I'm going to show the second, then I'm going to expect you to do the last one. I'm just going to put the answer, and you're going to see if you get it. It's kind of hard. But let's check it out. Quadratic form. 3 to the power 2x plus 3 to the x minus 2. How is this quadratic form? This kind of likens back to me asking questions like x to the 4th plus 4x squared minus 8. How do we know how to factor this? Because we're really thinking about it as x squared squared plus 4 times x squared minus 8. It's kind of like we're covering up this x squared and just getting this form of something squared plus 4 times something minus 8 and factoring. That's what's going on here. What's really going to unlock this, I'm hoping for some of you, is me rewriting this first term here. What is 3 to the power 2x? Well, this is 3 to the power 2 times x, which might be helpful if I rewrite it as 3 to the power x squared plus 1 times 3 to the power x minus 2 equals 0. Why am I writing this 1 times? Because it's going to help you see what's going on. I'm going to cover this up but undo this in a moment. If these things that I just crossed out were x's, x squared plus x minus 2, you would know how to factor this. You would say that's x plus 2 times x minus 1. But we don't have x. We don't have x. What do we have that we're squaring, and then what's our term in the middle? It's 3 to the x power. So we're not going to factor this as x plus 2x minus 1. We're going to factor this as 3 to the x plus 2 times 3 to the x minus 1. And from here, you really have to know how to solve these things, it's not just as simple as looking. And I'm kind of running out of space, so I'm going to write it up here a little bit. We have 3 to the power x plus 2 equals 0, which means 3 to the power x equals negative 2, which is not possible. Raising 3 to a power, you'll never get a negative number. But if we have 3 to the x minus 1 equals 0, 3 to the x equals 1, the x that makes that work is 0. So our solution to number 9 is just 0. Now I'm going to do the harder one, number 11. Then I'm going to ask you to do number 10. I'm going to provide the answer, but I'm not going to show the work for it. I'm going to see if you can do it. And if you have questions, you can always ask me today or Friday or later. So what's confusing about number 11 is all the way that things are written. 4 to the 2x power is the same as 4 to the power 2 times x, which we can write as 4 to the x squared. Raising an exponent to an exponent lets us multiply. Now 4 to the x plus 1, this one is tricky. We can rewrite this as 4 to the x times 4 to the 1. Now I'm going to rearrange those. You got to remember this adding an exponent really looks like a coefficient if we're thinking about multiplying. So I would write this as plus 4 times 4 to the x power minus 12 equals 0. And again, I'm going to do the same thing. This is the hard part, kind of rewriting it like this, but now that it's in this form, if I cross out the 4 to the x's and we pretended that it was x squared plus 4x minus 12 equals 0, I know you would all be able to tell me this factors to x plus 6 times x minus 2. But we don't have x squared, do we? We have 4 to the x power. So you're going to take what you understand of how this factors to something plus 6 and something minus 2, and we're just going to use 4 to the x instead of x. So what does this actually factor to? 4 to the x power plus 6, 4 to the x power minus 2 equals 0. And then to solve this, either 4x plus 6 equals 0, which means 4 to the x power equals negative 6, which is not possible. You can't get a negative number out from an exponent. Or we get 4 to the x power minus 2 equals 0, 4 to the x equals 2. This one you got to do a little bit extra work here. This is 2 squared. This is 2 to the first. We get 2 to the 2x equals 2 to the first, so 2x equals 1, or x equals 1/2. Or you could have been big brain and known that you take a square root of 4, you get 2, and that's 1/2. So our solution to 4 to the power 2x plus 4 to the power x plus 1 minus 12 equals 0 is 1/2. Now, what I would like for you to try to do is number 10. I'm going to write down the answer. I guess I'll write down the work. I mean, I'm going to give you my completed notes anyways. But it's really important. I'm not going to explain it. I'm just going to write down the work, write down the answer, and you'll see if you get it. So I'm going to pause, which means it won't pause your video, but you should pause and try it and come back and see my answer. All right, everyone, I lied. I did factor it. I did write these equations, but I want to talk about this one more time because this is kind of new. When you get 5 to the x equals 4, we can't get common bases. And when you can't get common bases, how do we solve for x when it's in an exponent? Turn it into a logarithm. So my very final thing I'm doing today, x equals log base 5, because that's the base of the exponent of 4. That is your exact. I don't know why that was so hard to get out of my mouth. That is the exact value. The approximate value of log base 5 to the 4 is about 0.861, approximately. So there's your approximate answer. There's your exact answer. That is solving equations with logs and exponentials all mixed together. There's another Math Excel assignment, 5.6. It opens today. I think it opens at 10. So if you're doing this really early morning, wait till 10, unless I remember to open it up earlier. It's due Sunday. We'll talk a little bit about this. We'll talk about our quizzes, and we'll talk about section 5.7, which deals with some application problems. Yay. Application problems on Friday. So see you on Friday, everyone.